Okay. Okay, so welcome to the final class. Even though we are not kind of done with the material in 5G and all. So in the interest of time, we'll conclude by looking at another interesting concept that is related to handovers. So let me get started. So let's look at this cartoon showing three base stations and one truck moving from the coverage of base station 1 to the coverage of base station 2. So that is the situation where we say that we need to have handovers where this particular truck, basically the user equipment which is inside this truck, has to be handed over from base station 1 to base station 2. So at the high level, yes, everybody understand what is handover and other thing. But if you actually dig inside, handover process is one of the complicated thing that happens in cellular networks. In today's class, we look at what are all the things that are involved when user equipment is moving and how handovers are kind of make the movement of the users kind of seamless and you don't face any issues during the data transfer. So if you look at in terms of the RRC states, I was talking about in the previous class that user equipment could be one of the three different states. One is RRC idle, then it is RRC connected. When there's not much activity for a certain amount of the time, rather than going back to idle state, in 5G NR we have something called RRC inactive. So in today's class, what I'm going to describe is something related to mobility that user equipment is undergoing when it is in RRC connected. What I mean by RRC connected here is the user is currently in active state. Again, what I mean by active state here is user is maybe either having a voice call or user is currently having a PDF session in which he is either transmitting or receiving the data. So during active data transmission with the network, if the user is moving from one base station to other base station coverage area, then we trigger the handover procedure to move the user equipment connecting to the new base station. And all of us understand that because of the mobility, the signal strength reduces. In this case, we say that it is with the square of the distance, it falls off. And with obstacles and other things, it becomes even worse. So the way it works out is the user equipment measures the channel quality. So in the case of 5G NR, the channel quality can be measured by just listening to the SS blocks. That means when user equipment is listening to SS blocks periodically with whatever the periodicity, let's say it is 20 millisecond or 120 milliseconds or whatever it is. It also looks at with what signal strength it is receiving SS block. If you recall, when I was looking at SS blocks, where we also looked at multiple SS blocks which are transmitted on different beams, and where user equipment will look at the signal quality received on each of the beams and will pick one of them on which it is getting good signal strength to camp onto the cell. Similar to that, even in the context of the handovers, user equipment does the similar procedure. Here, it not only listens to the channel quality of the currently attached base station, it is also called as a source base station. Like in this case, I can say that this one is the source base station and this is the target base station. And we also have one other neighboring base station here. So we have three base stations. In this case, user is in base station 1, moving towards base station 2. And there's also another neighboring base station, that is BS3. And user equipment, in this case, the truck or the user equipment inside the truck, he has no clue that user is indeed moving towards base station 2. Right? So what user equipment has to do is it has to listen to the channel quality. That means SS blocks information, which is transmitted by base station 1, base station 2, and base station 3. And initially, yes, the signal strength from the base station is higher compared to base station 2 and 3. But after a while, you see that the signal quality deteriorates for the base station 1 and it may be improving for other base stations. And depending on the logic at the base station or at the handset, we decide which base station to be the target base station. It could be the BS3 or BS2. The algorithm is not designed efficiently. If it decides to hand over to the base station 3, then it immediately leads to another handover because user is actually moving towards base station 2, or the connection could be completely failed. That is where you see call drops happening. Then you have to do the entire RACH procedure again to be able to re-establish the call. So that way, depending on the logic that we have at the base station and or even at the handset, so we can see these handovers becoming seamless, or the handovers become pain in terms of drop in the connection quality, or even the call drops altogether. And so far I was talking about handovers in the context of you losing good signal strength from the attached base station, and neighboring base station seems to be better than the current base station. But there's also other interesting scenario where you may want to hand over the users. This is in the context of load balancing. This is especially true in the context of macro cells and small cell, where you can say that I have a macro cell of this kind. Inside I have multiple small cells. So then what would be the cases where if I have even multiple such small cells inside one macro cells, the base station or the macro base station may be thinking of even handovering the user from itself to one of the small cell, because the small cell can offer better SINR, and because of the sparsity of the user density in that particular location, it may offer better data rates to the users. So that way the logic could be different, but at the bare minimum, we have to make sure that calls are not dropped. And if possible, we want to give better data rates and make the users happy. And when it comes to 5G NR and even LTE, the handovers that we have are called hard handovers. These are not soft handovers. What I mean by hard handovers are, these are break before make. So what is the literal meaning of that is, in this example, if you look at, user equipment is connected with base station 1 and it is moving towards base station 2. So in the case of hard handoffs, what is happening is, first user equipment is disconnected from base station 1 and then get connected to the base station 2. Yes, there is a small danger that the connection attachment to the base station may backfire. That is there, but that is the risk that is there both in 4G and 5G. In the case of 3G, because of the CDMA technology, there we used to have soft handovers, where the base station where the user equipment for a fraction of the time could be simultaneously attached with the source base station and also the target base station. But in the case of LTE and 5G, 3GPP decided to go ahead with the hard handovers, even though these are like a break before you make, but the design is done in a such way that you can able to do these hard handovers in tens of milliseconds, because it is happening even at a much lower rate, at a higher frequency than the rate at which even we make voice calls. Like when you are making voice call, typically every 20 millisecond, a voice packet of let's say 50 to 100 bytes leaves from your smartphone, and also you receive same thing from other end. Because the rate at which you are able to finish the handover is so fast that even we can leave with hard handovers. But later, as part of the URLLC, even in the case of multimeter, millimeter wave, where the coverage of the base station is even small, there we can think of even using multi-connectivity or dual connectivity with the primary and the secondary cells, so that user equipment can be simultaneously served using both the cells. That way, even during the handovers, still you have the chance that one of the two cells that you are connected still is available. It is very unlikely that you'll be disconnecting simultaneously from two base stations and attaching with two other base stations. That is in the case of URLLC and millimeter wave related use cases. But in general, it is break before you make. And we say that in these two networks, the handovers are of type UV assisted network controlled handovers. So try to understand what I'm trying to say here. Here the user equipment is only assisting, but it is not deciding the handover. At the end of the day, it is the base station. In this case, it is the source base station who is under the absolute control of which base station the current user should be offloaded or handover if at all such a situation arises. User equipment is only providing the channel quality related information to the source base station. That's why we call it as UV assisted and network controlled handover. So let me show you a couple of things which are very generic, applicable for any kind of network, not just cellular networks, any kind of wireless networks. We can apply this kind of criteria where we have more than one access point or the base station to serve the users. And when the users are moving in the coverage area of the network, then how to make sure that these handovers happen in a seamless fashion. So I hope all of you are able to see this very simple illustration, but it has a lot of meaning inside it. So let me try to explain what is happening here. So this is an example similar to the previous illustration where there are two base stations. So this is base station 1. So this is the base station 2. And I assume that we have a user equipment who is moving in this direction. It is not the time. So user equipment is UV is moving. And initially assume that UV is at here. And in the extreme case, yes, UV is moving from the tower where we have the base station 1 near the tower where the base station 2 is kept. So that is the kind of thing that I'm showing here. And here the y-axis. So this is the one that is showing the power received at UV. So does it make sense? Look at now the illustration. Again, it is like a cartoon. The signal won't pass down linearly. Yeah, depending on the kind of path loss model and other obstacles. Yeah, the power received could be non-linear. But in this case, I'm showing a very simple linear curve from base station 1 and also from base station 2. So look at these two curves. So this is the signal strength from base station 1. So that way when the user equipment is at this location, the signal strength that it will receive is the highest. But as the user equipment is moving away, like if I at all, let's say for example at this particular location, let's call it as point 1. If you want to know what is the receiver signal strength, yeah, you can. So this is the value, PR1. So like that, we can use this illustration to calculate what could be the power received if the user is at a certain location with respect to base station 1 and 2. Similarly, if you look at P1, we also have the case where the user equipment is also receiving the signal strength. Oops. Let's call it as PR2. So which of these two is higher in this example case? Now I'm showing an example where user has moved away from the base station 1 and reached a point P1. And at P1, the signal strength from base station 1 is PR1. Signal strength from base station 2 is PR2. So which one is higher in this case?
Signal from base station 1.
The PR1 is greater than PR2, right?
Yes.
And if it is like a smart handover logic, then the user equipment should be attached with the base station 1, or you should be moved away or reattached or kind of hand over to the base station 2. In this particular case, when the user is at P1, you want the user equipment should be associated with the base station 1 still, or you want it to be detached and attached with the base station 2.
Still attached to base station 1.
Right? So that's what you want, because you know what is really happening, because you have the global view of how the signal strength is varying with respect to base station 1 and 2 and where you are there. But neither the base station nor the user equipment may not have this kind of global view unless they do a lot of measurements and lots of reporting and try to deduce what is really happening in the network. But yes, in our case, yeah, we have this kind of a global knowledge. We can say that yes, put user equipment still with base station 1. I hope this point is clear to all of you. Now I'll go and talk about what are the different criteria that we can use to trigger the handover of the user equipment from the base station 1 to base station 2. So let's look at the case where, okay, maybe I will ask you guys again. So look at the illustration carefully and tell me what is the location in the figure at which the signal strength coming from the base station 1 is equal to the signal strength coming from the base station 2.
A.
So you are saying A, is it?
Yes, sir.
Okay, right. So A is the position at which user equipment is receiving same signal strength from the base station 1 and base station 2. So what do you suggest? Should we move the base station to the base station 2, or we want it to be still attached to the base station 1 at point A?
So as like moving to base station 2 will take more energy and overhead. So as both of the strengths are same, so it would be preferable to be connected to base station 1.
Right. So what you are saying is that if both the signal strength are exactly equal to the same, why to unnecessarily waste the resources? Let it remain with the base station 1. That's what you are saying.
Yes, sir.
But let's say you are a kind of have a smart machine learning algorithm where you are kind of predicting the path of the user, and you also know the terrain of the region where the user is moving. And currently you see that signal strength of these two base stations are exactly the same. So do you still say the same answer that you want to keep the base station user equipment to the base station 1, or you want to have a proactive handover, because anyway you know that the road is leading toward the base station 2 and user is kind of, let's say, using a car and moving at 60 kilometers per hour or something.
If the user is moving towards base station 2, like you said, an algorithm is there. So if we connect it to base station 2, then the handover would be more seamless and smooth.
Right. So that way, as you see clearly, it is not straightforward to decide whom to give the base user equipment, whether to retain with the base station 1 or reattach or kind of attach with the base station 2. It's all very, very fuzzy decision to take unless you have the complete view of what is really happening. So as part of something called measurement reports and configuration, user equipment try to provide as much information as possible without again draining their battery power, so that base station can take more informed decisions and able to reduce the handover failures and make the handover as smooth as possible. Okay, and take this case where so user equipment is kind of walking and currently is at the location A, and then he started putting one step back and forth. So what I'm saying that user equipment is just kind of moving like this.
It's like ping pong effect.
So this is called a ping pong effect because there's a small or negligible variation in the signal strength. But if you have the logic like this is where the handover initiation criteria comes into the picture. So the case one that I am going to show here is the pair, where the handover logic is look at the signal strength of both the base stations and you connect to the base station which is offering you the better signal strength. That is what the relative signal strength. The problem with that particular approach is when the user is just strolling in this particular region, so it leads to ping pong effects where user equipment kind of moving from base station 1 and 2 and causing a lot of signaling overhead, and it could actually lead to not only draining the battery power and also leads to the poor data rates for the user. So one of the solutions that one can think of to address that is adding certain threshold. So threshold is nothing but you not only want to see that relative signal strength are differing. We also want to make sure that either the current signal strength, like for example, if I call it as PR1 here, and if I call PR2, so PR2 means the power received from base station 2, and PR1 is the power received from the base station 1. Like in the case of LTE, or in the case of even 5G NR, we can say that we'll use SS block. You just monitor SS blocks, and whatever the power received while decoding SS block, that you set it to PR2. For the base station 1, you set it to PR1. So you have this PR1 and PR2, and you have set your plan to use a threshold. So one of the example that I wanted to show here is, you are looking at the relative signal strength, and also you are putting a threshold. So let's assume that the threshold that you are setting is if PR1 is less than threshold, and PR2 is greater than PR1. So this is the logic that I wanted to use. So the logic that we are having here is, we are checking the relative signal strength of base station 1 and 2, that is PR1 and PR2. So you want to see and come up with a scenario where not only you want to ensure that new base station is providing you better signal strength, and you want to go with the new base station only in a scenario where the signal strength that you are getting from the current base station is less than the acceptable threshold. So that could be one kind of threshold approach. Let's assume that I'm going with this kind of threshold approach, and I set my threshold as T1. And user equipment is currently at the location A. Or, okay, I will say that we are just crossed A. Okay, he is between A and B, let's call it as. User equipment is at a location between A and B, points A and B. And this is the logic that I am having, where my threshold is T1. So could you tell me, does it lead to handover or not?
Yes, it should lead to handover.
Right?
Yes, sir.
Does it lead to the handover?
Yes, it should lead to, because it is less than, the signal strength is less than T1.
Okay, you are right. And let's look at this case where user equipment is here. Then what happens? Does it lead to a handover or not?
Yes, sir. It's done.
So because the condition is satisfied at this point itself, one condition is satisfied, condition 1 or one of the condition has been satisfied here, and the second condition is satisfied just after the user crosses point A1, right? So because of that, beyond point A1, yes, it is kind of moving from the base station 1 to the base station 2. Okay, so let's assume, take the other case where my threshold is not T1, my threshold is T2, and the user is here. Does it lead to handover?
No.
So does it lead to handover or not?
No, sir.
So because the condition that is related to threshold has not met, right? So that way, when you actually trigger the handover, is very sensitive to the way you choose the thresholds. Like in this case, I'm talking about a threshold in terms of the signal strength, like I can have threshold, let's say anywhere from 0 to 15 dB. It is about the power received. So depending on how I tune my threshold value, I can see handovers are occurring at different points, and accordingly signaling overhead and UV power consumption and all kind of vary. And I can also have for the second case, I can also have another variant where this kind of thing. What I'm saying now, rather than depending on the power received from the current base station, here you are saying that if the PR2 is greater than threshold and if the PR2 is greater than PR1, then I can do that. That also could be one such algorithm one can think of. Yeah, so we looked at threshold-based approaches and also the simple relative signal strength-based approaches. And very often to address these ping pong effects, what we do is rather than just worrying about threshold and becoming a victim of choosing a poor threshold, we use something called hysteresis margin. Basically, it is nothing but an offset. So in this case, what you are doing is we are not only looking at the relative signal strength, you are making sure that signal strength difference between the base station 1 and 2, that means difference between PR1 and PR2 is greater than or equal to hysteresis margin or hysteresis offset, whatever that you said. So because of that, in this case, when the user is at point A, there won't be any handover. Even when the user is at point B, there won't be any handover. Only when the user is at point C, because you not only see that PR2 is greater than PR1, the difference between these two powers is greater than the hysteresis margin. So that way here you see the handover. And again, there is also fourth case where you not only use the hysteresis, you also use threshold. Okay, it's a combination of using an hysteresis margin and threshold. So depending on how do you choose threshold, in this case, if you say that my threshold is T3, not T1, not T2, then even the handover doesn't happen at point C, the handover happens at point D. Because only at the point D, the relative signal strength is higher for base station 2, and the threshold T3 has been satisfied, and the hysteresis margin is also met. So all the three conditions are satisfied at point D. That way, when the user is not reaching point D, then there won't be any handover when you are looking at this particular scheme. And I was just mentioning case where people also can think of using different kind of prediction techniques, which basically look at power received over the last few seconds and use that to predict the power in the future. And depending on the predicted power received, you can proactively decide whether to do a handover or not. Or you can also predict the speed of the vehicles, and also if you know the terrain and the routes on which the vehicles can move. If you are talking about speeds greater than what people can run, then we can think of varieties of techniques. In the literature, if you look at handovers and other things, there are hundreds and hundreds of research papers that have been published that basically talks about when to trigger this handover, when to hand over the user equipment from the current base station to one of the neighboring base stations.
Sir,
Ah,
so if a UV is between B and C and it is connected to A, like BS1, so after crossing or after touching B, it gets connected to BS2.
so he is between B and C, you are saying he is here.
Yes,
Okay. Okay.
yes,
Mhm.
yes, and it is connected to BS1. But when
Mhm.
it touches C and it crosses C, then it goes connected to BS2, right?
No, it all depends on which algorithm that you are
No,
talking.
no, this C, relative SS plus hysteresis. This C algorithm.
Relative SSP. Okay, C you are talking about. Okay.
Yes, C
Yeah.
algorithm.
Right.
So
Yes.
if the UV comes back from a CD space to BC space, then what happens? Will it again hand over to base station 1
Okay, what you are saying that user is currently okay. You are
between B and C, and then it goes between C and D, and then comes back between B and C?
between B and C. So that this is the case that you are talking about, right?
Yes. So if we use C algorithm, then what will happen?
So look at here. The handover has happened at this point, right?
Yes.
Okay. And now what you are talking about is the user has moved here. That means still the user, there won't be any handover. So it is still here. There is no handover.
Mm.
And now the user has come back here. And
Yes.
at point C, also the difference in the signal strength, if you look at here, the current base station and the other base station, in this case, okay, you are talking about, okay, now if I come back here, so if you look at here, you are not satisfying this condition, right? Suranjan, I think you are confused here. Look at here at this point, when you come back here. So tell me, PR1 is greater or PR2 is greater?
Peer 2 is greater.
Yeah.
Okay, so if for that condition, the handover won't happen.
Yes, yes, yes.
Okay, that condition is stopping it. Okay, fine. Yeah.
So that way you have to look at all these three conditions, and unless all three of them are met, then you don't trigger the handover back to the base station. And also we can use the timers. So not just to use the hysteresis offset. You just say that, okay, the difference should be like 5 dB for, let's say, 200 milliseconds. Then only you trigger the handover. So that also kind of takes care of some of the ping pong effects. Or few seconds, if you want to say it.
Okay, so late response basically.
Yeah. Basically, you're kind of delaying the handover, thinking that you want to reduce the number of unnecessary handovers. But
Right.
that thing could backfire depending on the situation where the users are located.
Right, sir. Got it.
And if you look at in the literature, I was mentioning about lots of research papers that propose different algorithms to trigger the handovers and other things. So they all can be compared based on different metrics, like just enumerating many of them here. So some other thing that you should be interested to know about here is call dropping probability. What is the chance that an ongoing call get terminated in between because of handover failure? So if you are coming with the different algorithms, yes, you can compare at the end of the simulation experiments or live experiments, how many call drops happened for different handover logics that you have. Probability of unnecessary handover. So that is also important. This is important in the sense you don't want to waste the network resources by spending a lot of them on sending signaling messages. Okay? Handover rate is how many handovers are happening per unit time in the network. So last two are very important. So let's look at what these are all. Handover interruption time. How long it is going to take for you to complete the handover, because during the interruption time, user is unable to transmit data to neither of the base station. If you're talking about previous example, source and target base station, you are neither able to transfer to the current base station and nor able to transfer to the new base station that you wanted to attach with. So that you wanted to reduce as small as possible. For example, in LTE, in 4G, so the handover interruption time is 40 milliseconds. And in 5G, we have some of the scenarios with some of the techniques. We can reduce this value to 0 millisecond by using dual connectivity and other cases. And there is also another metric, that is handover delay. Here the delay is not defined in terms of time, it is defined in terms of distance. Okay, so what is the meaning of handover delay? The distance the mobile moving from the point at which the handover should occur to the point at which it finally took place. So it is supposed to happen at a certain point, but you delayed it to kind of see that whether it is like kind of a unnecessary handover or not. That is the handover delay. If you stretch this handover delay beyond certain value, it could backfire as well. One has to be very carefully choose this parameter. So let's look at the trade-off that are involved when you are designing handover algorithms by varying the hysteresis margin and the timers. So this is an example where here the y-axis is the average number of handovers. And the x-axis is the case where the user is moving from the base station 1 to base station 2. So when I say 0.5, it means that UV is at equi from both base stations. 0.5 means user is 8. Basically, this is the point I'm talking about. This is the case. So then in this case, we say that it is 0.5. And as you see here, we are showing the things with the handover delay. Yes, at 0.5, if at all you really know that user is moving towards base station 2, you can actually trigger the handover. But in this case, we are kind of delaying the handover to the point A rather than doing at this point. So we are doing it at this point. So this is the handover delay. And see what is the effect of handover delay on the average number of handovers. So it has kind of reducing the average number of handovers. Also, you can see the effect of hysteresis and also the timers. As you increase the timers, as you increase the hysteresis and as you decrease the timers, you see that you can able to, not the timers, the thresholds. So you can see that these handovers can be reduced, the average number of handovers. So in the context of these handovers, I was mentioning about power received from the current base station and power received from the neighboring base stations. So what are all these powers? So there are lots of different powers in the 3GPP specifications. One of the most important thing being the RSRP, the reference signal received power. This is used for selecting the base station during initial attach. It is also used for reselection in case there is a better cell available, even when you are not moving. During the handovers, also we can use this RSRP. So RSRP is nothing but the average power that you are getting from these reference signals that are transmitted by the base station over the entire channel bandwidth. But it is like a power received, okay? It is not the signal quality, so that it is not providing you any signal quality. So the power received is defined in the range of -140 dBm to -44 dBm with 1 dB resolution. So rather than transmitting RSRP value to the base station, what user equipment does is it does something very smart, basically to reduce the signaling overhead. It maps this entire scale from -140 to -44 dBm to the range of 0 to 95. So that is like the integer values, so 98 values. But again, you don't transmit even all of them. So what you are doing here is see the mapping between the RSRP and the RSR and the power received. So this is the power received. So this is your RSRP. So when the power received is less than -140 dBm, the user equipment will send to the base station that, okay, my RSRP equal to 0. Like that, if it is in this particular range, then it is sending to the base station that I'm getting RSRP of 2 from the current base station or whatever the base station for which I'm trying to measure the RSRP value. Because the base station not only measures RSRP of the currently attached base station, it also measures the same value for the neighboring base stations which are operating on the same channel or even operating on the other channels. So finally, we have the RSRP 97, which basically means that we are getting extremely good signal strength from a given base station. In this case, it is greater than -44 dBm. Then you are transmitting RSRP as 97. So we have one more metric or parameter that we can use to provide information about the quality of the power received. So earlier thing is about just the power received. Now we can talk about RSRQ, that is the reference signal received quality. So that is calculated using this particular expression where N stands for the number of PRBs and RSSI is nothing but received signal strength indicator. Here you not only look at the power received from the serving cell, you also look at the power received from other base stations and other users, including the background noise that you are getting. Something similar to SNR, but not exactly the SNR. Okay. And here also you can see the mapping between RSRQ with the RSRP and RSI. Like for example, if the RSRQ value is less than minus 90.5, the base station will report that as value of RSRQ of 0. So what I'm trying to say is both the base stations and user equipment have these tables hard-coded in them. So whenever they receive these kind of values or observe these kind of values, rather than transmitting these course level information, it will, or the fine granular information, it gives the course level information. In this case, we have only 35 different values. Basically, it is hard to reduce the signaling overhead. So we also have this SNR that we have discussed earlier in the beginning of the course. Also, we have something called a CQI. So basically what we do is we measure the SNR for each of the PRBs using that power received and including the interference you are getting from other base stations transmitting on the same PRB, including the thermal noise that you are getting on a given PRB, and you convert into the scale of 0 to 15. So how we are going to use CQI is this is used in the context of selecting MCS. So when user equipment is transmitting these CQI values to the base station uses the CQI to decide what should be the MCS for the next downlink data transmission that is going to send to the user equipment. Whereas RSRP and RSRQ are the ones that are used in the context of cell selection and handover decisions. So this is also used in the context of cell selection and handovers, and these are used in the context of data transfer. So we also call it as this as adaptive rate control. Basically, here we are kind of selecting adaptively what should be the MCS to be used for the next downlink data transmission or transmitting the user data by getting the CQI information that is observed at each user equipment to the base station with certain controlling information coming in uplink. Whereas for the uplink, anyway, the base station measuring the channel quality at itself, so it can decide the uplink grants with whatever the transmit power control and MCS values itself. For the downlink, since the channel quality is measured at the user equipment, we have to force the user equipment to provide channel quality in terms of CQI to the base station. So this is what, if you recall, we discussed when we were discussing about how the scheduling is happening, where the user equipment is reporting CQI values and scheduling algorithm is deciding MCS. Let's come to the discussion on handovers in the context of 5G NR finally. So far what I was talking is in the general setting applicable for most of the wireless systems that you use. And let's look at handover management in 5G NR. So what happens is when you look at 4G and even the previous generations of cellular networks, the average cell sizes are quite larger. For example, in the case of 2G, we can have a base station which is covering a radius of 35 kilometers. Because at the time, not many people were using cell phones for making calls, and they have designed assuming that that kind of cell range is okay. But later, when we were talking about in the case of space division multiple access, the best way to reuse a given frequency is by reducing the cell size, where you can reduce the cell size by reducing the transmit power. So as you go from 1G to 2G to 3G to 4G to 5G, the average cell size is reducing. And this is even more true in the context of millimeter waves, where we have extremely higher path loss because of the nature of the waves that we are using there. So it brings altogether new challenges in the context of the handovers. Because the average cell size is small means even when the user is moving a shorter distance, you still end up having make handover from one cell to other cell. But if the radius of the cell is 35 kilometers, yeah, in the best case, even when you're traveling 70 kilometers, there is no handover. But if the cell radius is, let's say, 100 meters, there can be tons of handover that have to be triggered during, even when you are moving, let's say, from one place to other place where the distance is in the order of 1 to 2 kilometers. So that way, there are lots of challenges. First challenge is frequent handovers, which leads to higher handover failure rates. So higher handover that you are making, there's a higher chance of some of the handovers getting failed because of the way you do the handovers and your inability to successfully hand over the users all the time. The second issue is these frequent handovers also increase the signaling overhead in the network. That is a pure wastage of the channel resources. The third case is the increased handover measurements lead to increase in the power consumption at the user equipment. So compared to earlier generations of the cellular networks, the 5G systems are designed to operate on lots of different channels. The absolute radio frequency channel numbers, if you look at, there are lots of channels that ITU has defined for 5G operations. Your user equipment is kind of supposed to force listen to all these different channels to decide which channel is better if at all operator is getting licensed to operate on all of the channels. That has a negative impact on the power consumption at the user equipment because it has to do the channel state estimation on all the frequencies which operator is currently have license to operate these base stations. If it comes to the addressing the handovers, we have something called handover procedure, which has three main steps in LTE and 5G NR. The first step as part of the handover procedure is handover preparation. Preparation involves two main things. The first one is configuring the measurements at user equipments, where you decide what is the frequency at which user equipment has to monitor and what is the frequency at which it should report the measured values to the base station so that base station can take handover decision. So let's look at the illustration on the left hand side. So what illustration is showing here is that there are three steps that you see. In the step one, both the base station and the user equipment are kind of agreeing upon what should be the measurement configuration. That means what channels to measure and with what frequency to measure the channel quality of those particular channels, which base station has decided, and asking the user equipment to do the measurement. So that is conveyed as part of the RRC reconfiguration message from the base station to the user equipment. So make a note that all these things that I am showing here are done under the control of RRC layer. So RRC is the layer that is only there in the control plane, which kind of takes care of the radio resource control in user equipment and also at the base station. So this is RRC layer's responsibility in configuring the measurement settings at the user equipment by using RRC reconfiguration messages. As a response to that, yes, user equipment will respond that, okay, I will do measurement as you requested. So it is a kind of ACK that you're getting back. At a certain later time, depending on the kind of logic that we have as part of the handover procedure, the RRC layer at the user equipment will report the handover, not the handover, the measurements reports, the channel quality reports. For example, the RSRP, RSRQ of different cells on which it is currently listening to. So that information is conveyed as part of the measurement report. After that, the base station takes the handover decision. So based on the reports coming from the user equipment, it has to decide whether it is the time to do handover or it can wait for a certain time. In that case, it waits for further measurement reports and decides whether to take handover or not. So once it decides to do the handover, it sends something called handover request and gets acknowledgement from the target gnode B. The source gnode B sends the handover request to the target gnode B. Target gnode B does certain processing and send the acknowledgement back. So these are the steps as part of the handover preparation. So then we have something called handover execution. As the name says, here we are kind of asking the user, okay, it is the time for you to switch from the current base station to the new base station by doing, let's say, RATCH procedure. Finally, we have something called handover completion, where the UPF is a kind of forced to send downlink data from the source base station to the target base station. And after that, we can release the UV context, all the signaling state and all the UV state that is maintained at the source gnode B can be released so that user is completely moved away from the current base station to the new base station. So at the high level, these are the steps. I will explain in the following slides how these 3 steps have a lot of inner steps with lots of signaling messages between different entities in the network. Before I go talk about the handover procedure, let's look at the measurement reports in 5G NR. So as I was mentioning, if you recall, so this is a measurement report, the MR. So there are 3 types of measurement reports 3GPP has defined. First one is the periodic. We can say that every 20 millisecond or 10 millisecond, you tell me what is RSRP or RSRQ of the serving cell and also the neighboring cell. That could be the one setting. Another thing is event triggered reports. So rather than periodically sending these reports and wasting the channel reports, send me these reports only when certain conditions satisfy, like PR2 is greater than PR1 or PR1 is greater than or less than threshold 1 or PR2 is greater than threshold 2 or something like that. And there's a third case where the base station is forcing the user equipment to send the report. These are called on-demand or blind reports. Let's look at the event-triggered reports. There are 6 such trigger events that are defined in the case of 5G NR, where these 6 reports are specific to events are specific to the 5G cells. And there are 2 more events which are defined where the user equipment will monitor 4G cells. So that I'm not showing it here, but it is similar to what we are discussing here. Let's look at what is event A1. Event A1, whenever this particular thing is triggered, it is basically telling that serving cell is becoming better than the threshold. Serving cell becomes better than the threshold. Event 2 basically telling that serving cell becomes worse than the threshold. Again, this is whenever this condition has satisfied, the user equipment is sending the measurement report. So the measurement report contains A1 event or A2 event, so on A8 events. So based on the information coming through these events, the gnode B takes handover decision. So this is the second case. So, okay, it may be a bit surprising why we have to report when it is better than the threshold, right? So this is the kind of informing to the base station that maybe I'm experiencing very good signal strength from the serving base station. Then I can decide not to monitor the neighboring channels and waste my power. That kind of information can be conveyed to the base station. That is the meaning of using event A1. Event A2 is what we expect anyway, where you see that in this case, the signal strength is worse than the threshold T1, let's say. And event A3 is where neighboring cell is becoming better than the special cell by a certain offset. So like that, I think some of the events are not shown here, but there are 6 of them are specific to the 5G cells monitoring, and there are 2 specific to the 4G cells monitoring. So let me show you an example. This I'm showing in the context of LT, which is already implemented in NS3, but you can assume same thing is true even in the case of 5G. Even we can think of implementing this as part of the NS3 5G NR module in case if it is not already working. So let's look at what is happening here. It is called something called A2 A4 RSRQ handover algorithm. So let's look at the state diagram or the flow diagram that you see it here. This is the first step. The base station is receiving measurement reports from the user equipment. In this case, it has received event A2 and event A4. So what is event A2 and event A4? Come back and see it here. Serving cells becomes worse than the threshold. That means signal strength from the, basically here it's like a PR1 is less than T1. That's the kind of thing it says. That is A2. So what is A3, A4? ER2 is greater than T2. Is that clear? What is event A2 and event A4 are conveying to the base station as part of the measurement reports? Is it clear?
Yes, sir.
Okay, let's look at now this state diagram. First, the base station is getting these two events in this step, okay? Then look at what is the conditional check that base station is doing. It is checking whether serving cell RSRQ is less than or equal to serving cell threshold. In this case, yes, it is true. That's the reason why you have got this event A2. So then it has to look for the neighboring cell with the best RSRQ value. In this case, I'm talking about RSRQ, not RSRP. And in this case, you found one neighboring cell. So in this case, let's assume that event A4 has informed about one or more neighboring cells for which that condition has satisfied. The PR2 is greater than T2 is satisfied for, let's say, 2 base stations or both of them. Then what you have to do? You take PR2 and PR3 one after other and you compare with PR1 and take the difference of these two. PR1 minus PR2 and you check whether it is greater than the offset. If not, then you take PR1 minus PR3. So like that, for each of the neighboring cells, you are checking whether this thing is satisfying, where you are kind of having a offset. If it is true, then only you do the handover procedure. You are triggering finally the handover procedure. Any doubts on this part? Is it clear to all of you? How we can use A2, A4 RSRQ handover algorithm to start moving user equipment from serving cell to the neighboring cells, which is providing you better signal strength in terms of meeting the threshold T2 here. And also maintaining that the difference between them is greater than certain threshold.
So what is a special cell?
So special cell is a kind of thing. So like if you look at 5G NR, so we have these dual connectivity, secondary cells and other things, right? So in that context, they are defined. Secondary cell could be like ordinary cells as well. So this is the kind of meaning that is given. Okay. So let's come to the handover procedure. So here I'm talking about inter-GNODB handover procedure. So where you are moving user equipment from one base station to other base station. Yeah, you may be wondering why I'm emphasizing inter-GNODB, because I will tell you what are all other types of handover that are possible in 5G NR in the following slides. For timing, yes, we are looking at the case where user is moving from source GNODB to the target GNODB. The first step, as you see here, is the handover request. Handover request is sent over XN interface and it carries the CRNTI of the user. It also carries the target cell ID And it also carries information about the data radio bearers that user equipment is already having with the cell, with the source base station. Try to understand why I'm saying we have to provide this information with the target node B. Source node B. See what is happening here is already you got a measurement report. So after the measurement report, you have certain logic running at the G node B, like for example, something like this. And the G node B has decided to trigger the handover procedure. So handover procedure here has 4 major steps. One is the handover request. In the handover request, what user equipment is telling is, okay, I want to hand over certain user to you. How do you identify the user? We identify the user using CRNTA, cell RNTA, okay? And the identifier of the new base station is also provided over the handover request. So you may be wondering how it is possible to get what is the target cell ID. So can somebody tell me how the source base station decides and knows what is the target cell ID? So this is nothing but PCI, the physical cell ID of target genome.
Does the UE tells the source G node B this information that from which G node B it is getting a good signal?
Yes, yes. Yes, I was mentioning, right? It not only reports the signal strength from the serving base station, it also reports the signal strength from the neighboring base station. So how does it know whether it is my base station or the neighboring base station? By looking at PCI values. So that
And
way,
SIB5 also does.
the measurement report includes PCI of source. It also includes PCI of different neighbors, neighbor 1, neighbor 2, and all, along with the RSRQ values. Yeah, Madhuri, you are asking something. What is it?
So one of the SIBs also have this value like neighboring cell information, something related to handovers.
One of the SIBs.
SIB 2 or 5, I don't remember the exact value.
You know that. So what you are saying is true. So that is helping the user equipment to monitor neighbors. How does it know which are the neighbors? Yes, you are right. SIB, I think SIB 3 and 4, if I'm not wrong. So far, I think one of them is for 5G and other one is for 4G. In SIB 3 and 4, the serving base station tells to the user equipment that, okay, these are all the neighboring base stations that are available on 5G and 4G. So once the user equipment knows that information, then it listens to these channels using something called measurement gap. So during this measurement gap, what happens is the base station doesn't serve any data to the user equipment. So it is in the order of like 1.5 millisecond to even to 6 or 8 milliseconds. During this time, UV stops sending and receiving any data and start listening to the neighboring base stations and observing what is the power received from those neighboring base stations. So how it is listening to the neighboring base station is nothing but it is listening to the SS blocks of the neighboring base stations and getting RSRP and RSRQ values. So if the base station asks it to report RSRP, it will report only RSRP. If not, it will also report RSRQ values to the base station as part of the measurement reports. So that is the measurement report carries what are all the physical cell identities of the neighboring cells for which the user equipment is able to get certain signal strength. So that is conveyed as part of the handover request to the target G node B. So what target G node B does is it does the admission control. Admission control is important in the sense if the target base station is already overloaded, it doesn't have enough resources in terms of establishing one more PDCP entity, RLC entity, and providing the channel resources, then it can even decline to accept the request of handover. In that case, source GNOD has to look at another neighbors who are satisfying or who are kind of closely satisfying the request to handover. Then it has to send handover request with other potential target base stations. But for the success case, let's assume that the hand admission control algorithm has accepted the handover request. Then we have the message 2. In this case, it is a handover request acknowledgement. So this handover request acknowledgement includes RRC configuration message or RRC configuration parameters, which are kind of forwarded from source GNOD to the user equipment. So it will pass some information. So this is a kind of relaying the same information to the UV as part of the message 3. So what is the thing that is carried in message 3, that is RRC reconfiguration, is, so this is also called handover command. So basically asking the user, okay, it is time for you to hand over. So here it contains that I want you to connect with target cell ID so-and-so, that is the PCI of the cell, okay? And if you recall, I was talking about contention-free random access. Also, I was talking about contention-based random access. Unlike contention-based random access, in the case of contention-free random access, preambles are pre-assigned to the user so that only one user will be using the preamble using one of the RACH occasion, so that this doesn't encounter any kind of collision. So that information is also carried. That is which preamble that user equipment can do to switch to the new cell by doing the RACH procedure. So that is also conveyed as part of the handover command, or handover command actually include RRC reconfiguration parameters. So finally we have the message 4, that is RRC reconfiguration complete, which is basically moving the user to the target GNOD. And if the uplink grant is allowing, the user equipment can also send data, user data, as part of the message 4 to the target base station. So this is at the high level what is happening as part of the handover procedure. So you can appreciate what I'm saying better if you look at this illustration. Here I'm talking about the same thing. Now you can see the 5G core network as well. So far I was not showing a core network, but here you can see the core network also playing some role. Let's look at high level what is happening one more time. Yes, we have done the measurement report configuration and getting the measurement report from the user equipment. And source GNOD has decided to do the handover. Then it has sent handover request, so where it is providing the information related to the QoS flows, and also it is providing the keys related to the user authentication. So because everything goes by encrypting the data, right, in the wireless medium. So all the encryption keys, all that also has to be passed on to the target GNOD. Then it is doing admission control. Also, you can see clearly we are using XN AP protocol. Here we are assuming that we have the XN interface available between these two. So because of that, we are able to use XN AP protocol to send the handover request message. As a response, we are getting handover request acknowledgement, which is basically forwarding to the user as part of the handover command. Handover command is nothing but RRC reconfiguration. So then we have something called SN status transfer. Here SN status transfer is nothing but sequence numbers, downlink and uplink PDCP, not PCTP, PDCP. are transferred from the source G node B to the target G node B. So this is important in the sense, now in the downlink, the data should be transferred or kind of relayed from the core network to the target G node B rather than going through the source G node B. So that way, whatever the PDCP instance that is running at the source G node B should stop continuing, but already it has certain sequence numbers, and also it may be trying to ensure in sequence delivery and other things. So in that context, you have to make sure that especially for RLC AM mode, acknowledgement mode, we have to provide what are the sequence numbers currently used and what is the new sequence number that is can be given to the new packets coming in the downlink and uplink has to be conveyed with the target G node B. That is the meaning of SN stated transfer. So then we have the data coming from the core network to the source G node B. So what happens is, in this case, it is doing the buffering because the link is not available with the target G node B yet. So a random access with the new cell is done here so that it can update its timing advance based on the new cell. Now RRC configuration is completed. So then we have something called a path switch procedure from the target G node B to the core network, which is basically telling the UPF stop sending here, start sending here. That is the meaning of path switch procedure. So that way all the new data comes from core network to the target G node B rather than coming from the core network to the source G node. So this is what happening so far. After the path switch, the data from the core network, but in the case of downlink, comes directly to the target G node. Finally, yes, we can release the UV context because already data is coming through the new base station. So we can release the UV context at the old base station. Okay, so let me explain this at even a more depth level by using this diagram. What I have shown here, what I have shown here, and what I'm going to show here is exactly the same, only the difference is the more finer level measures are being shown here. I wanted to take a look at what is being shown here in this slide by spending 1 minute. So then I will explain what is really happening here. So there are 12 steps. Okay, there is one 0th step as well. So there are 13 steps. So I want you guys to appreciate what is happening in these 13 different steps as part of the handover procedure, which are divided into 3 major activities. One is the handover preparation, if you look at on the right hand side. So then we have the handover execution. Finally, we have the handover completion. So these 13 steps are divided into 3 parts. Just look at carefully and tell me if you have any doubts on what is happening here.
So this admission control is the target G node B is getting ready to admit the flow from UE. The UE.
No, it is not about admitting flow from the UV. It is about accepting the complete UV along with all its flows.
Okay. Okay.
It's not about our flow. It is about accepting a user along with all its flows, whatever it is.
What does it use like to admit?
What
It
is
is
it?
like it is checking if it is belong to the same operator or like that.
Oh, no, it is not about the same operator. Here it is about whether it has resources available to admit one more user. See, each base station has limited capacity, right?
Yes, sir.
So in that context, we are talking about.
Okay.
Like for example, it is a QoS flows that are coming. Let's say user is having QoS flow. And this base station may have already given all its resources to other existing QoS flows, which are also high priority. In that case, it is better not to admit this user and better ask the source GNODB to try with other target GNODBs who may have spare resources available so that it can guarantee queues for this user's flows.
Okay, sir.
Sir, the handover completion happens, and then after we do the path switch request. In the diagram, sir. Like,
Yes, you are right, right.
so will there be any issue if we do it later? Uh, if in between these times, like handover completion and path switch request, some data is sent to UE, will the target G not be buffered it only?
Okay, so look at uh, where the data is getting buffered. So look, I think let's talk step by step. So what you are
Okay.
saying is at step 8, right? So
Yes.
step 8 and step 9.
Yes.
So look at by the time step 9 is happening, where the data is going from the base station, sorry, not the base station, from the core. Let's look at, let's simplify the discussion. Let's talk only about downlink. So
Okay.
downlink is from the internet, the user equipment is getting the data, which is so far coming this way. Maybe I can draw a picture. Okay, just 1 second. So take this particular case. I have UPF. Okay, and from the UPF, I have this is target GNODB, and I have this is the source base station, and I have an user equipment here. So initially, what is happening is the data is coming like this. And now, what is the example that we looked at? The user has sent a measurement report, and it took a handover station. As soon as the source base station took the handover station, it start buffering the data. Okay, and then what user equipment is doing? It is doing patch procedure. Patch procedure, the whatever that we discussed about sending preamble and getting random access response. Only the 2 steps are required because it wants to get only the timing advance of the new base station because it doesn't know what is the distance between itself and the new base station. So for that, to get the timing advance, it is doing the step 1 and step 2 of the batch procedure. Yes, it has done that part. And the data is still coming like this, and the data is buffered here. Let's assume that after a while, the handover procedure has completed. So let's assume that so batch is completed. Then the case that I'm talking about is the target base station is informing to the AMF the path switch message. Okay, and what AMF does is AMF will talk with SMF, that is session management function, so which in turn talk with UPF. Basically, it is telling, the SMF is telling to the UPF that from now forward to target, So then the data will start coming like this. Is that clear, Suranjan?
Yes, yes, sir. Got it.
So anyone else have any queries on the entire call flow that I'm showing it here?
Sir, what about the buffered packets?
Yes, yes. Okay, buffer packet is also the interesting case. So where the packets are buffered, they are buffered at the source base station,
Okay,
right?
sir.
So all these packets, so these two guys have what? They have XN interface. So all the packets will be exchanged over this interface and they will come like this. Okay, let's look at the call flow and I will ask you guys to explain step by step one more time. So I will explain the 0th step. So here what happening is as part of the 0th step, so we are kind of getting the U specific information maintained at the source node. That means the U context, where in the context, in this particular case, what I mean by U context is with what are the roaming related constraint, what are the access network related constraint, all that are kind of configured at the source GNOD for a given specific user. So that is what I mean by UV context. So then step one. So I think can somebody answer what is happening in step one?
The UE is sending the measurement reports, which consists of the RSRP value, RSRQ value.
Yeah, that is one thing. But one more thing is happening here. It is measurement control and report. By measurement control, the base station is telling to the user at what granularity it has to monitor and what channels to monitor and for what condition it has to report. All that is a kind of a configuration. After the configuration is done, yes, depending on the logic that we have, yes, you will be transmitting these A1, A2, A3, whatever the event that are happening. These are mostly like a triggered based events. Okay, can somebody tell me what is happening in step 2 and 3? Step 2 and 3.
In step two, after measuring the measurement controls reports, the sources base station decides whether to hand over the UE from it to the target,
To
and then
one of
it
the potential
sends.
target base station. Okay. And step 3, what is happening?
They're sending it. The request is being sent.
To the one of the identified things.
Yes.
See, during the handover decision, it may actually look at the information related to multiple neighboring base stations. Finally, it has decided that, okay, so and so base station is the one that I should hand over the user. So that is the target GNOD. And by keeping the identifier of the target GNOD, in this case cell identifier, we are actually sending the handover request. So can somebody tell me what is happening in message 4 and 5? Message 4 and 5. Nobody? I don't know how many are there still.
The
Okay, around 13 people are here. Okay, you can answer, please. Hmm.
The base station is basically seeing if it has available resources to admit the UE, and if yes, then it basically sends a acknowledgement to the source saying that it can admit.
But acknowledgement carries something very important. That's what I was telling. The PCI of target, right? So what is the physical cell identifier of the target cell? And a preamble to use for RACH. message 1. So that is conveyed in message 5 from target G node B to the source G node B. So that user equipment doesn't have to listen to all the system information like SIB1, SIB2 and other thing. So we don't have to ask the user equipment to go and start listening to SS block and go and start listening to SIB1, SIB2 and other thing. So whatever is needed for it to quickly get started is conveyed from target G node B to the source G node B. Source G node B in turn forwards that message as the handover command, that is the handover command, which is nothing but RRC reconfiguration message. So now what is happening here, you see, the user equipment is detaching from the source cell and it is doing synchronization with the target cell by doing the 2 steps of RATch. So because it is given an exclusive RATch preamble, even whatever the application it uses, there won't be any collision. And in this entire illustration, can somebody tell me from what time onwards the source G node B has to start buffering the data?
After RAM handover completion.
After?
Oh, okay. You're right.
After 6, I think, like after source destination has told UE that you should get connected to target base station, then from that point onward it should start buffering the incoming thing, like from the UPF, whatever data comes it must put in the buffer.
Any other answer other than what Suranjan said?
After sequence number transfer, data transfer is there.
After what? After?
This SN status transfer.
After SN status transfer. The sequence, that is PDCP sequence number.
Yes, sir. PDCP sequence number.
So you are saying that here from whatever the message that is receiving from the UPF, it has to buffer it. Yes, that could be one thing, but look at here, even after step 2, look at here, what is happening after step 2? It has decided that we have to move the user to the new base station. And so G node B, to be more safe, it can decide to keep all the packets in the buffer rather than sending anything over the air. And it has to do step 6 anyway because there is no choice. We have to send step 6, and that can be sent maybe using, let's say, BPSK or QPSK, because you want to make sure that, yeah, user will at any cost will receive the handover command. But that could not be the case when you want to transmit the user data. There could be a lot of data. So that way, even at step 2 itself, it is possible for you to start buffering the data. Yes, you can do at any time after step 2. This is completely up to the implementation by the manufacturers, whoever is making the base station code. Okay.
Sir, is there any possibility that the step 4, the admission control, does not succeed and the handover request doesn't get acknowledged?
Yeah, I was mentioning, right? If the target G node B is not having resources, it will send handover reject message as message 4 or as a reply to the source G node B.
Okay, so in that case, the mobile user will face call drop or...
Again, here there are 2 cases. What if the source G node B has other neighboring cells information, which also satisfying the handover condition?
Okay.
That means what I'm saying is, if there are 2 neighboring cells, you are trying with the neighboring cell 1, but he is saying that I am busy, then you are checking with the neighboring cell 2. If it all neighboring cell 2 is also satisfying your requirement. If the neighboring cell 2 is not meeting your threshold requirements or whatever the logic that you have kept, in that case, there is no way you can hand over the user to any of the neighboring cells and the user is really going farther away from the source G node B, the link will break, and again you have to restart the entire RAG procedure to reconnect the user to the network.
Okay, that time it will start from the initial cell search,
The initial cell search,
like
yeah,
yeah, like
is
listening
active,
to the SS blocks, everything
and the ongoing call will be dropped.
dropped. Yeah.
Ongoing PDF session or the data session, whatever that you're having, so that is gone.
Okay. Okay, sir. Yeah.
And this is the one that I was talking about. Step 7 is where we are providing the sequence number information about the uplink and downlink PDCP entities to the target G node B, so that it can start using it can resume with the same sequence number if it is in the case of downlink. In the case of uplink, it can check whether there are any out of order packets and other thing. And if needed, it can ask depending on the scenario that you have. So now look at what is happening here. So this is important. I want you to pay attention to this. The user data is coming from UPF still to the source G node B. And now what source G node B is doing is important. So it is actually immediately forwarding to the target G node B. So look at here, even before the user requirement finishes batch procedure with the target G node B, as soon as you receive acknowledgement, like look at here, as soon as you receive this one, handover request acknowledgement, the source G node B can start forwarding the data which is buffered. This is in the case of downlink. Uplink anyway, whatever that I have at the source G node B, which I received from the user equipment, I can transfer to the UPF and it will go to the internet and wherever you wanted to transmit. So the issue is only for the downlink. That way, after the handover request acknowledgement comes in, you can send a SN status transfer message and start forwarding all the buffer data in the queue to the target G node B, even though actually the link is not established by doing the RAG procedure. So that's what you are seeing. The data is coming and getting forwarded using the XN interface, XNU interface. Whereas these messages will go over XNC interface, the control plane interface. Now finally, we have the RRC reconfiguration complete. Okay, that means the user is successfully connected with the new base station. Now look at what is happening here. All the buffer data which has already come here, so I can transmit to the user. And if at all the user has any uplink data, that also it can transfer to the new base station or the target base station. And whatever the uplink data that is coming from the user, it is forwarded to the UPF. So look at what is happening. The uplink data is coming from the user to the target base station. Target base station is forwarding it to the UPF. There is no problem. That's what we expect. Look at what is happening in the case of downlink data. Downlink data is still coming from the UPF to the source base station. Source base station is forwarding to the target base station. Target base station is forwarding to the. Basically, what you are doing, we are kind of relaying. So, are you able to understand this point? The downlink path is long, whereas the uplink path is straightforward.
Yes, sir. Got it.
And do you think this kind of thing you studied earlier as part of computer networks?
Yes, in ACN, in last chapter, it was on this topic, is wireless networking. There
No,
we
no, I'm
studied
not
this.
talking about wireless network. I'm talking about computer networks, internet.
Okay. Maybe not. Could not
Anyone else?
recall.
You all remember mobile IP?
Yes, yes, yes. For mobile IP, yes.
So this is what you do in mobile IP, right?
Yes, yes, yes.
So this is exactly what we do in mobile IP. There we call it as a
Home network and visited network or something.
the foreign,
Ah,
yeah,
foreign network.
yes, yes. So like that, you still getting the data. So the uplink data is directly going from the foreign network to the internet. But the downlink data, which you are getting from the internet, the home network will become your care of address. So still the data in the downlink comes through your home network. So what I'm showing is this part. Like if I have to draw a vertical thing, like if you are getting something from remote host, so this is the care of, this is your home network, and this is your foreign network, and this is your user equipment. So what I'm saying is, in the case of uplink, it will go like this. So here you got old IP. Old IP is given by this network, and the new IP is given by this network. New IP address. Again, I didn't talk about IP address here because there is no change of IP address because we are using the GPRS tunneling protocol in cellular networks. So only the CRNTI will change. I think here from this point onwards, it will get a new CRNTI that is assigned by the target cell. So earlier that was the old CRNTI. Whereas IP address point of view, it is still the same because IP address was assigned by the core network. That remains the same whether you are no matter which target node that you are connected with. So that way the uplink data will go like this, whereas the downlink data, because the remote host knows only your old IP. So all the routers in the internet will forward the traffic like this. So here what you do, once the data receives your home network or the care of network, so what you will do?
It will send the data to foreign network.
How?
Mm, it knows basically from the, like, there
So there
was
is,
kind of a transfer where the UE tells the foreign network where the home is.
so there is a tunnel using IP and IP. So you establish a tunnel where you keep the packet that is coming from the remote host inside the tunnel and you send it to the foreign network. So like that you send the data and the data will come here in the case of downlink. So this is what mobile IP about. Even though it is not deployed, but this is the mobile IP concept, mobile IPv4, mobile IPv6 that you study in internet systems. So something of similar you can see here, only difference here is there is no IP address change, but the data transfer wise, you can see that downlink data is coming in a loop like this, whereas the uplink data is going in straightforward manner. So now we have to do the path switching so that we can kind of take out the source G0 B in the path of downlink data transfer. So for that reason, the target G0 B is sending the path switch request to the AMF. So what AMF does is AMF will forward it to the SMF, and SMF will convey that to the UPF. So finally at the UPF, we are actually switching the path. Basically now we are telling to that for this particular user, you start forwarding to the target G0 B rather than the source G0 B. So now after it has decided to switch, what it does is quite interesting. It is sending something kind of marker packet. It is sending a marker packet. Basically, marker packet is like a special packet that is constructed by the UPF, kind of informing the source G0 B that I am not going to send any more data for this particular user to you. That is the meaning of sending the marker packet. The marker packet is conveyed using the traditional old route to the source G0 B. Source G0 B, yes, it receives, but it forwards the marker packet to the target G0 B. Now the target G0 B comes to know that, yes, this is the final message that I can expect from the source G0 B. Okay, that is what is happening. So then after that, all the data will be exchanged between the target G0 B and So the UPF, and the EMF is transmitting the path switch acknowledgement. Finally, we're actually releasing the U context information from the source genome. That way, even though I said it is a break before you make, the break before you make is happening only in the wireless. But if you look at in terms of the source G node B and target G node B, you are not actually doing break before you make. Here actually you are doing make before you break at the G node B level, but at the U level, you are doing the opposite. Okay, so I think we're already running late. Maybe I can take another 5 minutes and summarize a couple of few things that I wanted to say about the handovers. So this architecture you have already seen, where G node B talks with each other over XN, and they talk with core network using NG interface. In this case, NGU to talk with UPF, NGC to talk with AMF. And if you look at handovers, there are many different types of the handover. One is inter and intra-frequency handovers, where you are moving the user equipment from one channel to other channel, or you are moving from one channel to the same channel, but okay, no, N1, inter-frequency and intra-frequency. Okay, I think it should be B. Should be B. Here, user is moving from cell A to cell B, where cell A and cell B are operating on two different channels, channel N1 and channel L2. Case 2 is intra-frequency. The frequency is remaining the same, that is N1, but the cell ID is changing from A to B. The second one is inter and intra-RAT handover, moving from 5G to 4G, handovering from 5G to 4G, or from 5G cell to another 5G cell. Third case is inter-operator and intra-operator, like for example, BSNL cell to Geo cell, or one BSNL cell to other BSNL cell of, let's say, same 5G. And if you look at in terms of the RRC connected mode, so it actually UV participates in two types of the handovers. One is called beam level handovers using SS blocks and CSA reference signal measurements without involving any RRC signaling. There is no handover command, RRC reconfiguration messages coming from RRC layer to the user equipment in this case. They won't come. And this is all done using MAC and physical layer. The second case is what I was describing so far. That is cell level mobility, where the user is moved from one base station to other base station. But if you look at there are varieties of handover that are possible. One is intra-G node B handover. So the one is the intra-G node B handover. So when I say intra-G node B handover, you are moving from one base station to the same base station, but to the different beam. That's what the beam level handover that I'm talking about. There you are not switching from one base station to other base station. And the next one is inter-G node B handover, where you are moving from one G node B to other G node B, but your AMF is not changing and your UPF is not changing. Still you are with the same AMF and UPF. But we can also have the case where your UPF changes, but your AMF remains the same. And then we have other case where your AMF is changing and also your UPF is changing when you are moving from one base station to other base station. And other cases where only AMF is changing, but your UPF is remaining and your base station is changing. So like that, many handovers are possible in the case of 5G NR. So there are three special handovers which are related to the serial. So I guess we don't have time to discuss that. So this is a case where the base station is split into three parts as RU, DU, and CU. Then we can have three more different cases of the handovers possible. So let me show you this picture for you to quickly understand what I'm talking. It is very easy to understand. Just pay attention for 2 minutes. Look at the illustration and take the case where this is the example where you have the user equipment. It is moving from here to here. This is the case A. Look at the pictures very carefully. So what I'm showing you here is couple of, not couple of, yeah, 5 G-node Bs and one user equipment which is kind of hopping from one G-node B to other G-node B. And I have different AMFs, AMF1, AMF3 and 4. And I have UPF1, 2, 3, and I have single SMF. So basically this is example of one SMF connected with the 3 UPF and with the 3 AMF and 5 base stations and with a single user. Okay, this is the case that I wanted to show. So can somebody tell me, so what is happening in the scenario A, where the user equipment is moving from the starting location to the location where I'm showing in the picture?
The frequency is changing. The
Not
beam.
the frequency. What is that shape indicates?
Beam.
Yes, beam is not frequency. So when I'm talking about these beams, all the beams use the same frequency. F1, here you use F1 and F1, but I can serve user 1, user 2, user 3 with zero interference. Okay, got it?
Yes, sir.
So is it a handover? The base station is kind of using a different beam, using different antenna elements and others to serve the same user. So this is what I meant by the beam level mobility. No explicit RRC messages, only the physical layer and MAC layer is taking care of all the signaling to switch from one beam to other beam to serve the users. You are still connected to the same base station. So that is the intra G-node B handover. Now look at this case where the user is moving from here to here. Sorry, not here. So what is happening here?
It's moving from one G-node B to another G-node B location.
Right? But look at AMF point of view. What is say in terms of AMF and UPF?
The AMF is same,
Same.
the earlier one only.
And what about UPF?
It is also the same one.
So that is the scenario B. Now read the text. Inter G-node B handover, where it is intra AMF and intra UPF.
Right, right, sir.
So that means we look at in terms of the control plane traffic. Initially, the control plane traffic is going like this. Now it will go like this. The user traffic is going like this. After switching, user traffic goes like this. This is the example, is what I was describing, right? If you recall. Same UPF, and this is the source, and this is my target. In the call flow, this is what I explained to you as part of inter G-node B handovers. Your UPF is remaining the same, and only your G-node B is changing. So that is the case B. Now take this case C. So what is the difference now?
The UPF has changed, but the AMF is the same one.
So that is the case C, like intra AMF, inter UPF. So now we are switching from one UPF to other UPF. In that case, what happens is your SMF. What happens is your AMF informs SMF that it has to be given to the thing. Now SMF is informing this one, and this one will be talking with this one. So like that, a lot of signaling happens in the core network for all these things. Okay, so but at the high level, this is what I wanted to show. Now look at the next case, case D. Oops, not this one. So what is happening in this case?
Different AMF, different UPF.
Different.
All of them changes. The
All
G-node
of
B
them.
also changed.
So now you got not only the new base station, you got one more AMF and one more UPF to serve you. Okay. And the last case.
Only the AMF changed.
but not the UPF, right?
Yes, yes.
Yeah. I hope you understood the picture, even though it looks a bit
So, so
complex.
all of these cases can happen. Like there is no hierarchy that if this thing happens, the other thing cannot happen.
No, for a given user point of view, depending on how the operators are configured their core network. Say here I'm talking about the case where one SMF is connected with three UPF and with three AMF, and where certain number of base stations are connected with different AMF and different EFF. So in other
Right,
words, this is how the architecture, the topology of the operator that dictate which handover will happen.
right. So if such is the
PGPP,
situation,
gives all the options, and it
hmm,
is up to the operator to figure it out which base station should be connected with which core network elements. Depending on that, yes, different kind of handovers will happen.
right. So, yeah, got it.
So, any other queries from anyone on this?
Not exactly on this, but during handover, if the source base station becomes non-functional before the handover procedure has completed, then does the UE start from like the initial cell search because the target base station doesn't have any state with it?
Yeah, it has to do that. Yeah, that is in the extreme case. That's what it has to do. Yeah.
Okay.
Okay, so I think maybe I'll skip this part. The point I wanted to show here, you can watch the video that I have shared the link here, is the base station is also further split as part of something called a cloud RAN. So here I'm talking about things in the context of how to reduce the operators' expenses in terms of deploying the base stations. Operators want to deploy as many base stations as possible to serve as many users as possible and get as much revenue as possible. But again, not all of them are possible at the same time, isn't it? So to address that, we have the CRAN concept. So if you look at the high level, so maybe I will show you only one picture. So let's focus only on this part. So what basically it is talking about is, rather than thinking a base stations as something like a monolithic unit, I can split my base station into three components. One is called RU, which contains RF and lower 5. Then I have something called DU, that is called distributed unit, which contains RLC, MAC, and I5. Then I have this central unit, which contains HDAP, RRC, and PDCP. So today I'm talking about splitting the base station into three components. The link between these two is called the front hall. Yeah, it is called front hall. So here it is called the one between DU and CU. It is called the mid hall. So this could be like microwave link or it could be fiber link, depending on the channel bandwidth at the base station. So we have to provision that amount of the capacity on the transport network. It is like a optical network or WDM network or something. People use it to realize the connection between RUs and DUs and between DUs and CU. And it is also possible to connect multiple RUs to the same DU and multiple DUs with the same CU. Very similar to the way I'm showing here. Here, what you are seeing is multiple G node Bs are connected with EMF. But what I want to show is that if I have RU, R1, R2, R3, and R4, and I have D1 and D2, and I have C1, so these two can be connected with these two, one configure. I'm just giving an example, these two, and this C1 is connected with AMF, and this C1 is also connected with UPF. So this is for user plane. So this is for the control plane. So whatever I showed so far as a single unit here is kind of blown up like this here, where a base station is split into three components as RU, DU, and CU, where the DUs and CUs can be kept in the cloud or at the cell set, so that we can able to get the advantage of the centralization, because we can reduce the cooling cost and we can also reduce the maintenance cost because we have few active components maintained. So I will skip this part, and this is the test bed that we have in our lab, where we can use this open air interface to realize this kind of serial and test bed on x86 machines. I want to show this picture to explain the handover that happening in the context of inter-DU and intra-CU. So look at this example. I have one 5G user equipment which is moving from cell 1 to cell 2. The cell 1 is connected with, so when I say cell 1, it is my RU, okay? And this is my DU, and this is my CU. Yeah, this is my CU, okay? Yeah, this is another CU that we have, CU2, and this is CU1. So this is DU1, and this is the DU2. So in this example, what you can see is the user equipment is moving from cell 1 to cell 2. So this is the PCI of the cell 1, and this is the channel number, and the cell group ID. So all that are given here. And here, as user equipment is moving, the RU1 is connected. This is RU2. RU1 is connected with the DU1, and RU2 is connected with the DU2. And whereas DU1, okay, DU2 is connected, okay, DU2 is connected with, okay, this one, and yeah, DU1 is connected with the C1, okay. So in this example, what you see is your CU is not changing, whatever that is out there. And because it is possible to connect with the same CU, like in this case, it is the CU1, because this is also connected here. But your RU changing to something new and your DU changing to something new. So whatever that I was describing about at AMF and UPF level can also be brought into within a cell, because now cell has been disaggregated into RU, DU, and CU. Okay, so the last slide for today and also for this course is, if you look at, we looked at various different concepts in the context of handovers. Some of them require moving the user from one base station to other base station. Some of them require moving the user from one beam to other beam. But if you are looking at reducing the handover interruption time to 0 milliseconds, then we can think of using dual connectivity, where user equipment is connected with at any time with the two cells, and most unlikely that the handover procedure is triggered for both the cells simultaneously, so that even if the one link is under repair, or even if it is breaking, still you have other link available. So because of that, there is no interruption, or there is a call going to happen seamlessly. And there are also lots of new techniques that have been proposed in 3GPP. For example, in release 16, so they come out with something quite interesting called Dual Active Protocol Stack, DASP, handover. So DASP can be easily understood if you look at the picture on the right hand side. Again, I have source base station and target base station, and I have the user equipment. So in this case of DASP, I need to have two stacks running at the user equipment, but with a common PDCP, because PDCP is the one kind of takes the data from different RLCs and tries to merge them before giving to the higher layer. That is the case that we are talking about. So what is the motivation behind this dual active protocol stack? So this is also kind of similar to multi-connectivity and dual connectivity, where I can have one 5G, this could be 5G, or I can have one 5G and 4G, or I can have one 5G and Wi-Fi. So like multi-rat dual connectivity option that I'm talking about. So this concept has been applied as part of DASP here. In all these cases, we need to have two stacks running at the user equipment level, and we can do this link aggregation at the PDCP layer. So what is being conveyed in this illustration is, if you go back, you come back and look at this illustration. So if you look at here, in this region, the user equipment stop transmitting any data after it is receiving the handover initiation command. Like in the step 6, it has received handover command from the source GNODB. After that, what it is doing? It is doing the RAS procedure and trying to connect with the target GNODB. So what that's kind of telling is that till the user equipment finishes the RAS procedure with the new base station, it can be let transmitting to the source GNODB. That is the meaning of this. So look at here. So when it comes to the downlink, what happens is quite interesting. Data comes and sent in this link, and data is also basically what you are doing is you are doing a kind of duplication. So anyway, using the sequence numbers, the PDC player can identify the duplicate packets and discard. That way we are kind of increasing the reliability in the case of downlink. When it comes to the uplink, transmission of the uplink PDCP data packets continue to happen till RAT procedure is completed in the target cell on the source base station. Only after the RAT procedure is completed in the target cell, then only you switch uplink from here to here. That's what they attach. Then there's also have something called conditional handovers, UV-based handover, and there's something called even ratchless handover, because ratch is a kind of taking couple of steps. That means one round trip time to be doing the timing advance. But in the case of small cells, you don't have to really do the timing advance because the propagation delay is very negligible. Then you don't have to do even the ratch procedure. So there are lots of papers in the literature, and I don't have time to go through, but I wanted to share some of them. So all of them talk about how you can do things smart so that you can able to reduce the overhead of doing the measurements at the user equipment, so that you can save the signaling overhead and also save the UV power. And also you want to make sure that handover failures are minimized and interruption time is minimized as much possible without ping pong effects. So all these are the things that people try using a different machine learning technique and different algorithms at the user equipment level and also at the GNODB level, where we can also bring in some of the core network elements as part of other kind of handover that I was talking about to make the handovers as robust as possible. So these are the some of the references. I think this particular spec talks about access and mobility management services stage 3. And this is one of the interesting survey paper that is talking about the handovers not only in 5G but also talks about the 4G handovers as well. You can see what is the difference between 4G and 5G. Only some of the events are added extra in the case of 5G, and we have the beam level handover that is also added in the case of 5G, which was missing in the 4G. And also we have these CRAN related handovers that are also new. Yeah, that's all I have. I think, yeah, we're already too late, sorry. But I think I thought of concluding the course, at least by covering the handover part. And this slide is showing you something related to the 4G handovers. But again, you can go through the links, but you can see that the majority of the steps that you see are kind of same in 4G and 5G. So it is a kind of extension of what has been done in 4G. Yeah, somebody's trying to say something.
No, sir. Yeah.
Okay, so any final comments? So we are done with the course finally.
Thank you, sir. This has been a really good course.
Thank you.
It has been awesome. And today only I read that Airtel has held its first 5G trial in 700 megahertz band in like nearby Kolkata with
Oh, in
Nokia.
India, Airtel, huh? Is it?
Yes, sir. Airtel with Nokia core.
Okay, okay.
And I heard that Jio and Vodafone also tried it in Pune or somewhere else using Ericsson's packet course.
Oh yeah.
Hmm.
That was.
Yeah, a lot of trials are happening, and even Geo also claimed that they they have their own in-house or homegrown 5G solution that they wanted to apply countrywide. But they're all waiting for a spectrum to be, because 5G spectrum is not at auction, and the government is kind of still debating how much to charge for the 5G spectrum. And some cases, yeah, they reform the existing spectrum as 5G spectrum, and they also open up new spectrum bands for the operators to start operating or providing 5G services. So I guess sometime next year we can start seeing some of this happening related to the 5G deployments in India. But in our campus, we are already doing something called CVTX, the cellular VTX, as part of the Suzuki project. Maybe I will talk about this later. You can see the experiments happening in our own. Like Madhuri, whatever you are saying, yeah, IIT Hyderabad is also doing these kind of trials to demonstrate some of the use cases related to the collision avoidance on Indian roads.
Sir, can we be a part of that thing?
Yeah, definitely. Yeah, all of you by default are included. And yeah, hopefully you guys come back by end of this month. Then you can physically participate. We have purchased 10 vehicles, and so we have engineers from different countries kind of trying to set up the system where they're integrating these PTX radios on Baleno vehicles. And the field trials will start something time from January, February, March, and we're planning to conclude by April next year.
That's great. So, if, like maybe we will be able to come onto the campus in January. So,
Yes. We also have the
according,
project. I think Harinder is part of that project, Tihan. So there also we have created a test track for autonomous navigation where we have track with all kind of obstacles, slope, and simulation of rains and other thing is getting ready in our campus. So to look at the use cases related to the autonomous navigation and driver assistance for VT, using VTX technologies.